Hello, hello. Good evening. Welcome, everyone. Welcome to all of you here in person, and welcome to those of you joining online. It's wonderful to see you all. For those of you who don't know me, I'm John Oxendorf, professor in architecture and civil engineering. We begin with a land acknowledgement. MIT acknowledges indigenous peoples as the traditional stewards of the land and the enduring relationship that exists between them and their traditional territories. The land on which we sit is the traditional unceded territory of the Wampanoag Nation. We acknowledge the painful history of genocide and forced occupation of their territory, and we honor and respect the many diverse indigenous people connected to this land on which we gather from time immemorial. And now it's my pleasure to introduce the Edward and Mary Allen Lecture in Structural Design. This lecture was endowed for perpetuity with the goal of bringing the world's leading structural designers to bring their work and their philosophy of design to our campus each year, and even more, in addition to the lecture, to share time with students. And again, this year, our lecturer was able to be here for the week, spending several hours last night critiquing design projects by structural engineering students, and then many hours this afternoon discussing projects by graduate students in architecture. And so this really continues an important tradition which has become an annual event here, where each fall we're able to bring a leading voice. And this is all due to the generosity of Ed and Mary Allen. They're both longtime educators, strong supporters of students. And I must say, for me, it's especially important and personal to be able to introduce this lecture, because I arrived at MIT 20 years ago, and I met Ed Allen just when I arrived, and was essentially assigned to teach alongside Ed Allen, a first structures class by then head of department Stan Anderson. And I'll always wonder, Stan, I'm asking you, Stan, was it because you didn't think I could do it on my own, or because you knew the great hand of Ed Allen in education? And it was such a good fortune for me to be able to teach alongside Ed for a few years. And I just frankly learned so much from this person. And although Ed left us 2 years ago, the fact that the lecture series is going strong, we're able to gather together here in person. And because of their generosity, we'll be able to do this for generations of students into the future. And I'm so pleased that we're joined tonight by members of Ed and Mary's family, including Mary Allen. So please join me in thanking Mary and Ed for their generosity. And I know you're all here to learn about the work, so I will stand aside and pass the microphone to my colleague, Professor Caitlin Mueller. Please welcome Caitlin Mueller.
Good evening. It's such a pleasure to be here. Thank you all for coming. I'm delighted to introduce tonight's speaker, Jürg Conzett. Jürg Conzett is a world-renowned structural designer whose thoughtful, artful approach to the engineering of bridges and buildings engages history, culture, nature, and a playful application of deep mechanics expertise. Conzett studied civil engineering at the EPFL and the ETH in Switzerland, graduating in 1980. After finishing his engineering degree, he made an unconventional choice, joining the office of Peter Zumthor as an in-house engineer, where he contributed significantly and creatively for 8 years until he left in 1988 to begin his own engineering firm, which today is called Conzett Bronzini Partner. His engineering design work spans across material systems and typologies, often in timber, concrete, and stone, revealing new structural forms and details with freshness in each project. In 2011, Jürg came here to Cambridge as a visiting professor at the Harvard Graduate School for Design at the invitation of then Dean Mohsen Mostafavi, which we were all very grateful for. Mohsen Mostafavi wrote a seminal book in 2006 about Conzett's work. For those of you who do not know it, I highly recommend trying to get a copy. I looked today, it's $700 on the used book market, so maybe ask one of us to borrow it, but it's an incredible book. It's entitled Structure as Space, Engineering and Architecture in the Works of Jürg Conzett. And in that year, in 2011, when he was here in Cambridge, we were enormously fortunate at MIT to also benefit from this engagement. And we were lucky enough to bring Jürg here to MIT to participate in design and research reviews, in project discussions, and long conversations about the history and the future of structural design. And at that time, I was here as a PhD student, and it was an incredibly formative experience to get to spend time with someone of your ingenuity and intellect and wisdom, and I was very grateful for that then and now. This week, we have been so grateful to have you back here in Cambridge, spending time with our students and faculty with this engagement. We have all benefited from your generous interaction with students, with us, with all of us through reviews and conversations. Thank you for this precious time and wisdom, and also thank you again to the Edward and Mary Allen Lecture for making these experiences possible for our community. Finally, thank you all for being here for this really special event. Please join me in welcoming our speaker, Jürg Conzett.
Good evening, and thanks you, Caitlin, for this introduction. When I was here 20 years ago, I remember I started the lecture saying I had a long journey to come here, and so it will be a long lecture. This is still valid, somehow. Some weeks ago, I listened to the radio to an old speech by the psychoanalyst and psychiatrist Aaron Ronald Bodenheimer, and he said some really provocative things in the way observing is one of the most stultifying activities there is. We should learn again to think. It was a lecture about politics, about postmodernism, and somehow I was very touched because I always told the students, I always told the young engineers in the office, go outside, watch, observe what happens. And now this kind of philosopher, Bodenheimer, tells this is the most stultifying activity. I have to think about that. And maybe we can take that as a motto for this evening. It came to my mind that Wilhelm Ritter, professor at ETH, published that scheme in 1899 as a possible analysis of Ennebig's reinforcing system for reinforced concrete. And he said he imagines a truss with diagonals in the concrete under 45 degrees. And finally he said it would be good to prove that with some tests. So this was thinking, this was speculating. And finally he anticipated today's standard. So I think this can be an illustration for the power of thinking in the sense of Bodenheimer. Applying this to the design process, I tried to schematically represent that by these three elements. Okay, thinking, writing, and then precisely drawing. That's one possibility. On the opposite, sketching, following visions, dreaming, two completely different ways of obtaining a design, or designing by convention. This is not bad. This is something we often do. You take a precedent, you adapt it to the problem you have to solve. It's good for that way if you know history. I think Ed Allen was a thinker. He was passionate in bringing together the visible, the form, and the invisible, the forces. He was not only a thinker, he was a connoisseur. Only lately I found this book on stone shelters by Allen, with his passion for Italian craftsmanship in these walls. And retaining walls were always very important for me. Look at this strata in these walls. And this is one of the walls I analyzed for the Russian railway. Also limestone, stratified with always one smooth surface and one rough head. And look at that corner, how this is built and how it matches the natural rock face and how the upper part is done with these interlocking vertical stones. I'm very passionate about such things. Another very beautiful photo by Ed Allen from Italy. This interplay of road and landscape. And I will come back to that photo at the end of the lecture. And also that has some familiarity with some own works, these stairs and these transitions, not always very clear between the built and the natural. A great book, these stone shelters. Coming back to form and forces, I feel highly indebted to that culture established by Allen with this passion for rationality. I think there has been some changes in the attitude of engineers around 1980, which were also responsible for my shift for some years to the architect's office. And I maybe can illustrate that. Bruno Reichlin showed me the writing by Edgar Allan Poe, how he conceived his poem, The Raven. And obviously, if poet or detective or whatever, at that time, 150 years ago, everybody wanted to be an engineer. Today, the engineer has disappeared, even in Robert Meyer. Everybody wants to be an artist. And I illustrate that with two bridges. This is a bridge not far from my home, an immense arch bridge, spanned 265 meters, built by cantilevering out successive phases in concrete. This is the moment where the two cantilevers meet. It was the result of a competition, and the jury praised the slenderness and the transparency of this design. And certainly this is an impressive work. Looking at the longitudinal section, you see from here till here, the arch has the section of a full rectangular concrete section, almost 3 meters high. The arch has a continuous curvature. You have an immensely span from here to here. So, looking at that, it's very clear. There was a will to a form a priori, which was then done by the calculating engineers to realize that intentional form. So this is a piece of art. Another bridge, which at first gaze may look similar, but only at first gaze. It was the result of another competition last year, also a big arch bridge. The position of the bridge could be chosen by the engineers. And so, okay, happily, Schleich-Bergermann and our firm won this competition with the shortest bridge of all the entries and the longest span. This is already a concept. Huh? Shortest bridge, longest span. This implies that the impact on the landscape is very small. Whereas other projects had a shorter arch, but a longer bridge and a bigger impact. So the jury here decided for the smallest impact into the landscape, but looking at the bridge in detail, it has significant differences to the Tamina Bridge. It's of steel, lightweight steel. It has a polygonal arch. And everything is conceived to the uppermost rationality in this position of the bridge. Next week, I will have a serious debate with Andreas Keil from Schleich-Bergermann, because Keil, he wants these pillars to be parallel. I want to be them radial. And Ed Allen certainly will help me in that discussion. So another example to show this tradition which goes on. Huh? Now it's high time to present a little bit what we are doing. This is Switzerland, Zürich, Chur, St. Moritz, Bondo, we will come back on that place, Poschiavo also. And these are my partners. Gianfranco Bronzini on the right, we collaborate 30 years. Now, Peter Henry, the youngest, 45 years old. Josef Dora, also a very long companion. Myself, 66 years, the other 55 years. This is a good distribution of age to guarantee a certain continuity. So for today, I thought in a first part, I want to have maybe a receptive chapter on personalities which have influenced me during my lifetime. And I will present of each of these three people one project which is important for me. Then we will make a little intermezzo, short intermezzo. And in the second part, I will present some own projects. And as, like in the beginning said, as I want to talk about thinking, this can be very short. I just show the most important aspects of these projects. And then finally, the Orido di Cavaglia and the Bondo infrastructure. These are two projects that deal with landscape, which I would like to present maybe in a bit broader way then. Okay, I used many photos from friends or from the internet. Christian Menn, you might know as the engineer of the Bunker Hill Bridge over Charles River. He was professor at ETH. He was my professor too. And in the 1960s, he invented this elegant arch bridge system with a post-tensioned hollow box stiffening girder on the top and a very slender, rectangularly sectioned arch. I used this drawing for presenting our Soranzuns Bridge, but it's also very good to present Menn's Fiamala Bridge. You see this bridge over the gorge in a S shape, and here it crosses the old road in a very flat angle. And Mann's conception in the longitudinal section looks like this. And he said a big challenge was this crossing at a flat angle, a big span which dimensioned the hollow box section. And then he took this section over the whole bridge and added the arch, which is stiffened by the hollow box section. As there is this curvature in plan, he shifted these walls as much as possible away from the springs of the arch to have not too much horizontal eccentricities. You see it here, this is the last pillar, asymmetric, and after that, the driving way turns left. And on the other side, it's similar. And now he wrote something very important. These are the different sections of this bridge. And he said that once you have found the relationships between all these different elements, arch, pillars, and driving way, then the form-giving process reduces to choosing only a few parameters. And this is something which I consider as a conceptual thinking, which has very much fascinated me as a method of working. Robert Maillard, pioneer of reinforced concrete, he built this first deck-stiffened arch bridge in concrete in the world, 1924. It bridges an artificial lake. You see how high the water level can come. And for this reason, Maillard conceived all the submerged pieces very massive. And then he put this absolutely slender arch above it. And this was really an invention that had a large influence until now. In the literature, it is normally said that the bridge was built in 1924. It soon had problems with frost resistance, damages, and in 1932, only 8 years after its erection, it was restored the first time, and at that opportunity, one introduced these side walls to close the space between the arch and the stiffening beam. Also, by that opportunity, one introduced these granite slabs to cover the concrete from the intemperies. The bridge was not in a good state, as you can see. So, a local engineer said it has to be demolished, and they made a project for a new bridge. And there was a votation, and this was accepted by the local government. And only after that, some opponents came and said, hey, this is an important work. You cannot demolish that. And then followed a struggle for years with court and anything. It ended up that our office got the job to investigate the feasibility of a restoration of the bridge. This is the Lake Wackital with this bridge called Schräbach Bridge. This was the first big artificial lake in Switzerland. Maybe it was the biggest also in Central Europe, with this huge dam going deep down into the earth. A very ambitious project. There were architects from Zürich, Pfister brothers, who designed the crown of the wall. There was the director of ETH engineering department, Arthur Rohn, as a consultant. So really a great work. And Schräbach Bridge was part of that work. I inspected the bridge, spent many hours there looking at the damages. I mean, these walls, these are bricks. They have no structural action. Everybody agreed that a restoration would be the possibility, the chance to bring this bridge back in its original state, to enlighten the whole structure. That was like clear from the start. I found some intriguing things. You see, there is a line. It comes back here. And along this line, there is like a band, 7-8 centimeters, hammered concrete. It reappears under the bridge here, very clear. Okay, I realized this is concrete from 1924. This is concrete from 1932. And to have a proper junction between the two materials, the joint was hammered to just make it regular. It goes on and on through the whole building. Somehow I was fascinated by this pattern. Then the look from outside. Studying the reinforcing drawings, I realized the arch has no upper reinforcement. That Meyer did never again. This is a bold decision. And even if you could calculate that it could work, this is not such a good feeling. Made me scary a little bit. And then you see these cracks. And somehow at that moment, I was not so sure if this is a good idea to remove these walls. Of course, they are not structurally, but maybe rather psychologically, it helps to give a certain trust. Then, the archivist of the power station found material in his archive. Look at that. This is 1932. This girder is in a formwork. This explains the line I have shown first. I mean, this was a surgery at open heart. You have this thin arch, and this is the stiffening element, and they work on the stiffening element. They take away all the bad concrete. This is proof that the drawings are right. 1 bar, diameter 12 millimeters, all the 30 centimeters. That's not very much. And then, this drawing, not by Meyer, but by the power station company. A wall on one side of the section. And it goes on. This photograph. The oldest photograph of that bridge, August 26. Oh, the walls are already there. Who is the photograph? It's Wolf Bender, a renowned architect from Zürich, specialized in architecture, a renowned photographer specialized in architectural photography. He waited until the lake was full. He waited until there was no wind to have the mirroring image of the bridge. And this is not a photo just, this is a tableau. And after a while I thought, it's a beautiful image. Beside Meyer and his work, but as an image, it's beautiful. This bas relief of the bridge with these walls. And, okay, there are no written documents, but it was clear that was Rohn and the Pfister brothers, because they also had built bridges together at other locations, and they always had this neoclassical attitude. And as I said, this was an ambitious project. They just could not stand the Meyer little pieces. They made it in a decent way. But these walls are there for aesthetic reasons. And that changed my attitude another way, because this was not accidental. This was intentional from conservative architects, but good, interesting architects. And as I said before, for structural reasons, I was reluctant to remove these walls, but now also for historical reasons, for having this bridge as a testimony of discussions in 25, I came to the conclusion this must stay, this must be polished, this must be better. In the middle, these two were missing since 32. We thought of re-establishing that, and then I started to think, and thinking brought out that. These are the walls, and it's not a problem to make these small walls out of structural concrete behind these aesthetic walls, and we transformed the bridge into a Salginatobel system, which with a very small amount of concrete almost doubled the load-bearing capacity of the bridge. And it had the advantage that we did not have to care about the balustrades anymore. We tightened. There was an infill of concrete, I don't know why, but we exchanged that for, there were some bad elements in it. We replaced that and we covered it by an ultra-high strength layer of concrete to make the whole thing watertight. This is some of the most important thing. And as the owners of the bridge wanted to use it for transports of wood from the forest, they had a problem with the narrow curve, so we enlarged that curve on the south side. On the not so visible side, that was just a tribute to make the bridge usable anymore. And very important, always the mock-ups. My wife was a primary school teacher, and at the age of 30, she made an apprenticeship as a furniture maker, and after a while, she specialized in model making for our office. She makes so great models. So we tested the support of that enlargement on the model. 3 additional pillars looked not very convincing. 2, neither. That's not good. Enlarge the existing pillar in the background is better. Enlarge it with a skew face is even more better. So that was it. I presented the model to the conservationists of the canton and to the clients, and they all said, oh, this is very interesting proposal. And so, okay, I also showed that the cost of this was half of the new bridge. So we could do it. This is the reinforcement of these additional ribs inside, really not a big thing. And this is the finished bridge. Bridge restoration in Switzerland today. I mean, I got a letter from a colleague, what the hell do you here? And I mean, it looks so rough. It's not what people maybe expect from you, but I mean, we saved the bridge. We strengthened it. We tightened it. We saved a lot of money, and we said, this is part of the history of the whole thing. More than 90% is original substance. It has its original color. It's really the concept to make a patchwork of repairings. And if you don't like this image, you can see it in sunlight. Maybe this is a bit better, but I'm very happy about this whole story. And it was so interesting. It's maybe still not the most beautiful thing you can imagine, but this doesn't matter. It's such an interesting story about also Maillard and a certain failure and how what develops out of this and this kind of enemies in the aesthetic sense. Okay, this is Schrebach Bridge. Peter Zumthor, I worked in his office, as you have heard, and one interesting collaboration was the Capluta San Benedetto. It was a competition. He drew the plan by hand, and I proposed to follow a mathematical function for this plan. And after some debates, it ended with the Lemnis cut as a directrix form for the plan. It was 1986. I had my first personal computer. I made a spreadsheet for calculating the length of the Lemnis cut. It took 1 hour to calculate that at that time. And then we divided that length into 37 pieces to get a rectangular, a regular distance of the pillars. I did the work twice because after a while we found out it's not the pillars which are important, but the windows. So now the windows are regularly on the whole length, and this explains that distribution of pillars at that point. Okay, so far done. Now, the rafters are perpendicular to the contour line. This defines the intersection points along the central axis. Then, the incline of the rafters is 1/3, constant for all the rafters. This defines the longitudinal line of the roof. Finally, this is exactly the same procedure as Menn did with his bridge. We developed a system of interdependencies, and finally, it was to choose length, width, height, and slope of the roof. And then the thing was fixed. So I think this is interesting. The same way of thinking in a bridge, in a chapel. Okay, now, as I said, some intermezzi. The power of figures. Otto Wagner built this bridge in Vienna in 1900 for the elevated railway of Vienna. It's interesting to have these noise protection barriers out of steel plates in the shape of a curtain, of a textile curtain. Otto Antonia Graf, he collected all the drawings, all the works by Wagner in several volumes. And one volume is dedicated to Wagner's teachers, Sickart and van der Nul. These teachers built the Arsenale in Vienna. What follows now is the analysis by Otto Antonia Graf. From the plan, he comes to the entrance door, and finally, he shows how every rectangle of this door, every hexagonal ornament corresponds to one point in the plan of the whole area. This is interesting. After studying some of these analyses, I went to a Viennese self-control. This is a bridge we did in Belgium, a lifting bridge resting on sandstone pillars. This is the longitudinal section. You have a height of 4.75 meters from the floor to the uppermost stone slab, and the slabs are 25 centimeters high. There are 19 panels, and there are 19 slabs. I remember when I told the draftswoman, hey, put one piece more, it looks better. But this was all. This was, of course, not a conscious decision, but it's somehow intriguing how you are dominated by things you don't know. One of these stone slabs, turn down the height, multiply by 12.167, you have the whole bridge. There is an error of 41 millimeters, which you have to excuse, but again, these are things. The falling water bridge, a slender stone arch. I spent a lot of time determining the rise and the thickness of the slabs and the amount of post-tensioning. Finally, what came out, also, I realized afterwards, a beautiful triangle, 49, 41. That's more interesting than the 3, 4, 5. A suspension bridge over the Rhine River we built some years ago. Also, when finished, I prepared a presentation. I had rebuilt George Washington Bridge in the scale of 1/12. It would be ridiculous to start work like this, but to find out how deep this George Washington is carved into my mind, it's such a funny thing. Okay, let's stop with that, but this is maybe a conventional design, as I mentioned at the beginning, but conventional not means very easy. It was hard work to master all these details, all these different phases of erection, but it also had its qualities, the footings of the stiffening girder, and the cook-in-chief who proudly presents his steelwork fitting together. Okay, so far so well, but I wanted to give some remarks about feeling uneasy. This was, at the beginning, the head with just rectangular lines on the cable. Of course, this looks odd. And later on, we found out that the forces, of course, do not go perpendicular to the cable, but there is an amount of friction because this is another slope than here, and so the longitudinal force in the cable changes. So we corrected the shape to these black lines. And still I had the feeling of something neck-breaking, which I could not explain because everything is so clear. And it was only later that I found out that the deformations are very big during the construction process. We intended to put the steel socket here to avoid kinks in the main cables. And now, if you look at that, the intersection point shifts, and the resultant forces is outside, or almost outside the section. Okay, once the problem was seen, we could handle it. But this was like something present in some way as an inquieting thing which had to be analyzed and rationalized to overcome. The finished bridge has handrails on a height of 1.30 meters because it's used by cyclists, and I also was not so sure if this is a good height for a handrail, but as you see, people like it for their elbows. Okay, last part of this intermezzo. cultural background. It's not only that there is a structural culture for bridges and so, but they can also be background for another type of culture. So the 5 arches here, the 5 arches there, the king of pasta, Pietro Barilla, with his artists. Architect, scenographer Piero Ghirardi, who designed a lot of clothes, made a film for these Barilla pasta with Mina Mazzini as a cantautrice. And here she sings Mai sarà così on the roof of the Fiumicino airport in Rome, a structure by Riccardo Morandi. This is maybe the only country in the world where structures are background for singers. Okay, now I come to some own projects. The first is a holiday house. There we had to build a wooden roof on a polygonal shape, and we used analogies to reinforced concrete. You see the house, you see the rafters in different spaces. Now the structure goes like that. There is a concrete plinth. Inside there are wooden posts, walls, a roof structure. The ridges here are not supported because the architect wanted to have free corners. There is a first layer of horizontal beams. Over the supports, this is densified with some short pieces. Some panels, and then second layer, rafters. Again, the distance is differentiated along the needs of the structure. So this analogy to reinforced concrete is very economic because you put the material exactly there where you want. So this is the inside aspect of this house. Shell structures in another way. This was a competition with Marcel Meili, Markus Peter. This is the site. On this site you see 8 strong pillars, and over these pillars we proposed a shell structure, not only for the roof, but a shell structure for the whole house. So in section, it looked like that. I mean, here, everybody speaks about sustainability. And I think all the examples I showed until now were concerned with minimizing material. And also, I think if you take that seriously, we have to reinvent the shell structures in concrete, which are so efficient. Okay, the plans, the sections. And this was the final presentation. Of course, we did not win. No. The winner was David Chipperfield with a neoclassic, serious building. If not shelters, at least some folded works in concrete. A bus shelter, 4 independent structures, pure concrete, without any watertight layer, because they are independent, they are post-tension, they can shrink, they will have no cracks. This is the formwork going on. reinforcement. Concrete. Finished. Thin plates of concrete, I think in a beautiful relationship to the station building by architect Max Vogt, who made a series of remarkable buildings for the Federal Railways in Switzerland. Evening. The new concrete, the old concrete in the background. The old concrete and the new concrete in the background. Okay. An old common theme with John Caminada, the log buildings that move vertically. Here he had the job to create a guest house with big holes in the lower stories and rooms for guests in the upper part. So it's like a hybrid structure, high-tech in the lower part and old-fashioned in the upper part. The problem of the big holes was solved like this. You have sort of a king post reaching up 2 stories inside the inhabited part. But as there are these logs which move vertically, they are just guided by the king post. They can shrink. They are fixed here, only here. You see the tension beams of the king post here, supporting the slabs. And the logs outside are partially supported by outside pillars in front of the windows. Assembly of the king posts, the whole in its rough and in its finished state. The 2 pairs of king posts are filled with the logs without direct mechanical junction. And this is the finished structure combined with the staircase. So this was a vertically moving house, now a horizontally moving house, a schoolhouse made of concrete, 2 stories, and we proposed to hang up the outer facade on these bridge bearings here to make them breathe. It's a 70-meter long house. You see it here. So all that is monolithic, no joint. And all that can move. In summer, it expands. In winter, it shrinks. Some small post-tensioning. So I think also this is a contribution to the durability of that building. It's not only an aesthetic or something like that decision, but it will not crack. It has no reason to crack because it can move. So all this is hanging. These are tension elements, and also the sheds are monolithically combined with the facade. Inside, it's a very beautiful cured concrete. Okay, I come to the 2 last landscape projects, the small one first, Orrido di Cavaglia. This is the Bernina Railway crossing the pass on 2,200 meters here and then going down, 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 down. There is a plain called Cavaglia with a small gorge at its entrance, and then the train goes on to Poschiavo. And I was asked to do a path through that gorge. It was only about 100 meters long, but a very peculiar gorge. This was coming from the surveyor, the level lines. You are lost with such a drawing, of course. And as always, first we built a model and with the model we could find the alignment of that path. Just over these abysses of these gorges, there is a part of a protruding rock supported by pillars, which create some kind of a balcony. There is the railway bridge where we cross underneath on another bridge. The central aspect of this project was to use local stone in different ways. So we have the sawn local stone for the new bridge under the railway bridge with that transversal arch. In the first phase, this was traditionally masonry. Finally, we put there 3 big pieces, or big, 1.30 meter, 3 pieces of stone like this, a bit like in a Gothic cathedral. We tested that, of course, because it's somehow a bold structure. This is the balcony with these masonry pillars. Then there is a descent with stairs in a rather conventional way, like this. And we had one basic principle, which maybe is a bit astonishing in the whole context. We never went into the rock with the masonry. We did not want to have water going through the joints inside the rock and creating damages by frost. So you always have a concrete plinth. Sometimes it must balance a little bit on the rock, but this is very hard rock, which allows for that. But there is never a direct contact between masonry and rock. So it's like here, you see the concrete coming out some centimeters of the rock. And yeah, also this was a nice, small experience in stone. Finishing with that project that occupies me the last 2 years very much. This is Valle Bregaglia in the south of Graubünden. You have the Upper Engadin here behind Maloja Pass, and then it goes down steeply to Chiavenna. And many things have happened in this valley. This is Stampa, a little village where Augusto Giacometti, Giovanni Giacometti, Alberto Giacometti were born and working. This is Castasegna, the frontier between Switzerland and Italy, where Gottfried Semper built one of his few villas. And so it always has been a very fascinating landscape. Now here, this is Bondo, this is the Maira River, and this is the Bondasca River. Again, Bondo, the Bondasca River, Pizzo Cengalo, and now in 23rd August 2017, this rock face bursted. Many thousand cubic meters of rock fell down, and the impact of this mass was so intense that the groundwater was pressed out of the soil and created a flood. Bright weather, and here the flood comes. And the people in Bondo had a few minutes to flee, and here it is. It killed 8 hikers, but in the village nobody was hurt, and yeah, it could have been even worse. But you see the tunnel entrance. The road went through here on a bridge, down there. The old road still intact. The connection between Promontonio and Bondo went through Punt there. And they dug out the material day and night because they knew there will come more material. In fact, 3 times it came And this is the so-called punt, the old bridge. Here first damaged and then in the next flood completely destroyed. At once there were taken emergency measures, and then for creating a definitive solution there was a competition which we could win with a large group of specialists. And this project was based on a, of course, technical and robust background, but as well as on a cultural background. And this is a photograph from 1914. It's just called Heimat. It shows one of these stone bridges. It's this bridge here. And also in other incidents in the last century, they always rebuilt their stone bridges. This was very clear. Now our entry was to lift the road from this existing tunnel entrance and to span the Bondasca with a 65-meter span and then slowly going down again to the terrain. To emphasize the artificial character of this road, we proposed to build all with retaining walls of local stone. It's more or less the photo I have shown by Edward Allen at the beginning. So this is local stone. And finally, some contractors from the village, they said, we can use the stone out of this deposit of the catastrophe. And this was somehow a good thing that it at least gave some material for the new walls. And we had the advantage that we did not need to import the stones from somewhere. Of course, the bridge with 65 meters is not a stone bridge, but it's a concrete frame. And the frame has something to do with arches. We resisted the temptation to make a structure like a bowstring or something which goes up. And this was not only a technical decision, but also a cultural-based decision. So the longitudinal profile looks like that. The new road, almost horizontally, crosses the Bondasca Bridge, and then it goes down. This is Bondasca Bridge, right now under construction. And then we had to replace that small, nice punt. Here was punt, here. The road coming from there, crossing, going there. And then we started to try some positions, but with the need for a flood profile for the Bondasca River, it became so steep, 16%. And was not good. It was not good. And then I like to show you this example really for the way of designing by thinking. I just said we should not exceed a slope of 10% with these access roads. And now let's see what happens. The old bridge here, we try to start as far away as possible here. Okay, this is the plan. This is the 3D representation. So the access road goes here with 10% slope, and this defined that intersection point. We just varied this length, and we got to here with these 10%, and then the bridge is wrapped around this inclined cylinder which defines the flood profile. Yeah, that was interesting somehow. Unforeseen also in the program of the competition, but was not thought to put this bridge in this position. then we had the track tricks of some cars going here, which enlarged the access road at these 2 points. And so it created the kind of bracket, which is in a way very special, that you have an existing road and now you turn 90 degrees, go over the bridge, and then you turn again 90 degrees. But somehow this is what happened. It's a document of a destruction and the reaction on this destruction. And somehow this creates a viewpoint out of itself. And then we started to go more into details. At the middle, it's clear it's a trough section to minimize the structural height. And at the end of the frame, you need more depth underneath, and according to this inclined cylinder of the float profile, it's an asymmetric section. And it ended up like this. And somehow the bridge developed itself, because this is great. Here are the biggest forces from the curvature in plan. This very eccentric section is perfect for that purpose, but it just developed itself. Okay. Many months later, we had almost finished the drawings for it. We had studied it in a 3D representation. We had made the renderings and so. And then, again, we decided to make a physical model. Okay. Lydia is cutting out the piece for the bridge, which was a very complex thing. I had to draw, to make papers, there's developed lines, and so you see the plan, of course, and then here you see the lowest profile line of the girder, and you see also the upper profile. Now she makes slices to get the upper profile. So gradually this mock-up develops. Of course, this is completely anachronistic, but that's how we work. It may have been a reminiscence of the Schrebach bridge that in the competition we proposed to cover the walls of the trough by granite elements to emphasize the character of a footbridge. And this was very clear. And then in the mock-up, this is symbolized of this covering. We took it away and it was much better. But this was something we only saw in this mock-up and not before. An important decision. Then we had these intersection points like here, concrete, stone. And at the beginning we were very direct, but here it looks so odd. Also here, that's not possible. Finally, we realized that the access stone walls must have the same width like the parapets of the bridge. All that we found out only because we did that model. So that's the final version of the project. Actually, it looks like that. This is Punt on the scaffolding. From upside down, this is Bondaska Bridge. And 10 days ago, the butterfly leaves his cocoon. This is the parabola of the fifth degree for Punt, now realized. Okay. I thank you for your attention.
All right, thank you so much, Jürg. We're going to have a brief conversation here, and then we're going to open up the floor for questions. And we're going to aim to finish by 7:30, 7:35. So it'll be about 20 more minutes for those of you who are eager to hear and ask your questions. All right, so please, Jürg, thank you so much. Would you like to say?
Okay.
Great. Well, first of all, thank you so much for that incredible talk. The breadth and the history and the contemporary projects that you showed were, many of them were new for me, or maybe all of them were new, and it was really exciting to see all this work. I wonder if you can start a little bit by reflecting on your own education and on education of architects and engineers today. You shared with us a few days ago that you had a very strong formal education in engineering fundamentals, but it also felt maybe incomplete or in some way overly rigid, and so you had the second education in the office of Peter Zumthor.
Yeah.
Can you elaborate on that a little bit more and reflect on how that process worked?
Yeah, this was how it was in the 70s. As an engineer, you were trained to dimension screws and post engineering. It was very, very okay. I still use much of this material I got then, but how to design structures was just not our business. Somebody from outside told us what to do, or we made some proposals more or less accidental. And this was not existing, and I was suffering on that. And I learned, I was always interested in reading architectural journals and so, and I saw that architects are much more conscious of their work and their history and so on. This was the reason why I looked for contacting architects. I think today this has improved, but these were the dark 70s. Yeah, I think this was a special time. I think the first time that sustainability became an issue by limits of growth, written by the Club of Rome and things like that. And still we were in this old-fashioned kind of, maybe going back to the 19th century, engineers have to concentrate on their work because this is complicated, which is true. They should not be distracted by other things, but they should learn about drawing the polygons and so on. And this, in a certain way, was right, but in a certain way led to a dead end. I remember in the 80s when Calatrava came with his Stadelhofen railway station. This was extraordinary. This created so many discussions among anybody, engineers. Hey, is it allowed to do such things? And this was, at that time, really important as a kind of liberation. There are other possibilities to deal with that questions of structures and architecture and this relationship.
Wow, that's great. And what about architecture? I mean, obviously your education is formally in engineering, but you're actively involved in architecture. What are your thoughts about the education of an architect? What does an architect need to know?
I think Alvar Aalto said an architect has to be interested in everything. Yeah? Okay, no. Maybe this was one thing I learned with Zumthor in this Bauhaus tradition, that a building should be valuable on different levels. Of course, it should provide good spaces, but it should have a good impact on your feelings, but it should be a good structure, and it should be a good instrument for mechanical engineering. And this ambition is something substantial. I mean, maybe also in engineering works you have the visual things, but you also have the intellectual things. And this is both important.
I'm thinking of the triad that you introduced in the beginning of thinking and sketching and convention, history. Where do you see yourself engaging? You said you think Edward Allen was one who engaged in thinking of those three. How do you see your own work in that framework? In the triangle you showed, where do you see your own approach?
That's
in all of them.
Of course.
Yeah.
I mean, when Moisen and I did this book of Structure of Space, there is a chapter, abstract principles, and somehow this comes out from there, and that this is really intriguing. This Bodenheimer with his kind of observing is stultifying, but somehow to see maybe that observing just can be a compilation of empirical knowledge without a theory. Maybe he's right in that aspect, that this is not the whole history, just observing. And okay, this is relatively new for me, but maybe a theory is always an anticipation. Maybe a theory is a speculation. It's not in the laboratory that you develop theories. But I think this could be true, that you develop theories by thinking and then you go and to try to verify it.
In the project you showed with the folded plate, the concrete folded shell structure, the roof, you made a provocative comment that there's a lot of interest in sustainability, and perhaps if we're truly interested, we should reconsider typology, right? More than maybe minor modifications to existing structures. We should consider typologies like shells that are known for being extremely lightweight and yet challenging to use in many scenarios today. How do engineers and architects confront that, do you think? You said earlier how to design, how do you know where the idea comes from? Traditional engineering education, it's arbitrary. How does one access these new ideas or old ideas that we've forgotten about to trigger these typology investigations?
Well, I think in some way, looking back to times where, for example, concrete was a very precious material, which was used in very conscious, small sections. I think this is interesting. It cannot be the future to make fixed labs just to hide the ventilation ducts in it. That's something which I think could be good. Also, we discussed yesterday with some students about hollow parts in a structure, which I learned is very dangerous when you cannot control it. But maybe it makes sense to introduce hollow parts and to supervise them somehow. We have different means today, and I think this is something we should rethink. What is the most efficient use of a certain material?
Maybe I'll open up the floor to questions if anyone has any, or otherwise I can ask more, but does anyone have a burning question in the audience? And there are two, if you do have one, please, oh yes, Paul, please come, do you mind asking it to the microphone here? Thank you.
Is the on?
It's on.
Oh, it's on.
Yeah.
It's on? It's on. Sorry, hi, great, fantastic. Thank you very much. So this is a sort of structural engineering annual lecture, and what we've seen with you is this sort of complete human being in your design approach, your technical thinking, the kind of the deep concern for architecture, space, program. You know, it's wonderful work that you've shown us, and you've also shown that you're quite amusing in many ways. I think we've enjoyed tonight. So my question is, in the work and how you've presented it, you've shown us your sort of technical ability and your deep thinking. How do you bring into your work, if at all, a kind of freewheeling, amusing, jokey, joy, sketchy approach? Where does that belong in your work, or how does it belong? Thanks.
It's maybe difficult to answer. Yeah. I think, okay, there is part which belongs to oneself and which is difficult to answer. But I mean, for example, the collaboration with Peter Zumthor was important in that sense that he works so long, so slow, not slow, but constant change, a constant critical reflection on what you are doing, which, okay, that can end in some kind of tension, but on the other hand, it can also create some atmosphere. What else is possible? What are all the possibilities we have? And I think this is something important. I told you yesterday, I think it was Charles Eames, and he was asked, why do you win these competitions? He said, we work harder. And maybe it's a bit like that, which on one side is maybe really harder, but it's also very joyful to try out and to think about and to check variation. Yeah. I mean, no, one important thing is you need the clients who allow you to do that. Without that, you are lost. And in a certain sense, we get projects of that character. And we don't do speculative things, or we are not maybe the right people for investors who look, not all investors, there are interesting investors, but investors who look for the short time profit. And so that's also a piece of freedom you have to care for.
Yeah, please, come down.
So just sort of following on the same theme, I'm just curious how you approach your proposal writing with clients. I mean, I'm a practitioner, so I'm bringing in the quote-unquote real world of contracts and money and collaboration with team members. And I'm wondering if you put it into your scope of work proposals, things like additional scope for collaboration, additional scope for iterations of design, which clearly costs a lot of money and time. I think for a structural engineer in particular, I once had the experience as an architect working with a structural engineer and trying to engage in an iterative process. And he got frustrated and he said, you need to hire an architecture consultant. In other words, meaning you need to figure all this stuff out and then come to me and I'll do the structural design once, And what you're talking about is a process where you're doing the thinking more than once. You're thinking about a lot of different ideas till you get to the right one, and you're working them out in different ways. So that's a question of, do you put that out there for the prospective clients in the beginning and say, this is what we do, this is the central scope of iterations or alternatives that we're going to look at. This is how much it costs. is that part of your process?
So how do you communicate to clients that your process is not a typical one-time engineering process? How do you create expectations and communicate value and cost in your contractual agreements and in communication? Is that fair?
Yeah, that's a good sign.
I think we work mostly regional, and so people know each other. And I mean, it happened that, like the Schrebach bridge, that we were called when there was really a conflict to solve this conflict. And then the important thing is that you find a solution, and not if this is the most cheap solution, which it was actually, but I think there are situations where people want somebody who can adjust things, or competitions are also important for us. And when you win a competition, then the client is positively to your project, and then you can go on. Of course, you have to discuss, you have to explain, you have to show. Still, I'm not sure if they will pay us the mock-up I showed for the Punt. Well, if they don't pay us, it belongs to us, and we don't give it to them. I mean, these are things which happen. There is some part you just also do like you need. Yeah, it's a question of negotiation, always. I mean, that's human. I show the things which were successful. And that's not always the case, of course.
Juliana, last question? Unfortunately, yes. We have an online audience as well, so thank you.
So you mentioned this triad of sketching, thinking, and convention. And obviously the path from thinking to realization of an idea is not a linear path. And I'm curious how you also mentioned that you engage with all of these each piece of this triad throughout the entire realization of an idea. But I'm curious how your engagement with each piece changes throughout different phases of project realization. So how do you make sure you're still thinking at the end of your project?
Yeah, of course, this is a schematic presentation, and simplification, but the importance of thinking was really something maybe a bit new, created by listening to that radio speech. Probably you could, for each step, if it's an overall concept, or if it's detailing a note, restart the same different ways of solving a problem. Also, a detail you can solve in a conventional way, or you can think on it, or you can dream on it. I think this is something that goes through a project and don't need to be always the same method. Yeah.
Thank you.
Okay, fine. Very quick question, and then we'll.
Thank you for your presentation. I liked the detail that you added of the first time you used a computer on a project. I'm curious do you have some thoughts on the role of computation in your workflow? Do you have strong thoughts about hand calculations versus computation? And yes, if you could talk about the role of computation in your and the use of computers in your workflow.
The role of computation. You gave a great example of in the early project with Zumthor. You used a spreadsheet to calculate the geometry.
Yeah.
What's your current attitude towards computation in calculations, and how does that fit in with other hand calculations or other methods?
Yeah, that's. I can say you need a big toolbox. Lately, I learned to draw on the computer in the 3D model, which is on a way fascinating, but I'm faster drawing by hand. And I'm a bit scared if young people today only depend on the computer. That's not good. I think rough methods, especially in the conceptual phase, can help you to see things. And I think graphical statics are wonderful to follow what happens. I could have shown some examples of spatial structures where we treated with projections of forces to understand what happens. And you see, I'm still intrigued by this Bodenheimer talk, but maybe the computer absorbs you from thinking. Sometimes I have the impression somebody took a system, he let it calculate it, there came some colored schemes out of it, they put some reinforcement where it was red, and that was it. And I have different ambitions. I think I think this was Sastafny who said when Maillard worked on the deck-stiffened arches, following theories, he should always have increased the thickness of the arch. But instead, he made it thinner to liberate it from bending. So, I mean, this is thinking, and this is understanding, and this is looking at where it should go and not be depending on results. I think this is like maybe what I can say. You should know what the machine does. And I think it's also like in statistics. Someone told you can establish a relationship between anything statistically. But when you want to use statistics in a good way, you have to foresee what you want to prove. And I think maybe this anticipation is the most important thing.
Wonderful, thank you very much. We're going to conclude with some final remarks from Professor John Oxendorf, but maybe first join me one more time in thanking Jürg Conzett.
Well, thank you all so much for coming. Thank you, Jürg, for a wonderful lecture as always, and it just makes me so happy and fulfilled to see Ed Allen's legacy being carried forward, and also to think of the memories of generations of designers coming here in 10250 to share their work and to inspire us. And so to the students in the audience, go design,